Hello, Science Alliance. Hello, I am Lara. I have a science degree and I'm trained to teach physics up to A level in secondary schools. So we're doing IGCSE physics and this is the last electricity lesson. So yeah, here goes. Let's do it. Next term, if you watch live, then after this lesson, I'm taking 2 weeks off for Easter and then we're going to start the waves module, which is a wonderful time to join in. This is the last electricity lesson, so a lot of the stuff I'm going to be assuming that you know because I'm assuming that you've seen the previous lessons. So you're welcome to stay, but don't panic if I end up saying things that you don't understand. Right, start a question. I asked you, where are the electrons in these different scenarios about to go? So this is a very useful recap. It'll help us with this lesson, but it's also stuff you need to know anyway. We've got here a petrol pump nozzle. Yeah, so petrol has come through this tube. It's come to this nozzle, and we've got some electrons that have built up on the nozzle here, and we've got a metal car that the nozzle is very close to. Here we've got some electrons that are built up on a comb, and there is a hand approaching the comb, and here we have a cloud with some electrons on it hovering above a hill. Where are those electrons about to go? Hopefully this wasn't too difficult, right? The electrons in the comb are about to go into the hand. Why? Why like this? Why? Well, hopefully you know by now that things that are negative repel things that are also negative. So two negative things are repelled by each other. Electrons that have built up on a comb, maybe because, well, probably because the comb is made of plastic, which is an insulator, you remember? Current can't flow through it, the electrons can't flow through the plastic, so you rub electrons off your hair, say, and onto the comb, they build up, and then when you come along, the electrons, they try not to make it that like they don't want to because they're not alive, but the electrons can travel through your hand. So they do, and you might get an electric shock. That's what that is. It's like electricity going into your hand. Particles in air rub against each other when a storm is brewing and electrons pop off, and then eventually the electrons build up so much that they end up going into the ground. That's what lightning is. And this scenario is super dangerous. So if the nozzle is made of plastic or something on the petrol pump, that's an insulator, and petrol is also an insulator, so it's kind of like the comb and hair situation. The petrol rubs up against the insulating material on the nozzle and you get this build-up of electrons, and when you put that next to your car, you've got this incredibly flammable liquid, which is the petrol, but also a spark of electrons, lightning, if you like, electricity jumping from the nozzle to the car, which is a very dangerous scenario. Why do all those things happen? Did you think about why? That's kind of the important bit. It's all about resistance, basically. So Earth, obviously Earth isn't positively charged. It's not that it's attracting the electrons in that way, but the Earth has just got a very, very, very low amount of resistance. Resistance is how hard it is for current to flow, and it's dead easy for the Earth to take on a few more electrons. Not going to make any difference. In the same way, well, we'll talk about the difference between Earth's resistance and your resistance a bit later on, okay? Here's a beautiful lightning rod from a post office in Hungary, apparently, built in the 1930s. This is one of the ways that people certainly used to protect their buildings. So beautiful building, you don't want lightning to strike it. You put this bit of metal higher up into the air and the electrons flow through the outside metal casing of the building instead of through the building. True fact, it was a trend at one point. I think it came over from France. When electricity was first getting sort of talked about by humans, you could get an umbrella that was apparently protect you from lightning because the electrons would flow through the metal pointy bit on the umbrella and then down a wire that was attached to the ground. Or you could get a dress if you wanted with a wire going down it. Yeah, not a good idea. Not a good idea. Do not try that at home. Right, to kind of change tack for a bit, but we'll come back to all that. Here's a graph. It's got time on the x-axis. It's got voltage on the y-axis. Not a trick question. If you were going to draw a wave that stayed at 2.5 volts on this graph, what would it look like? If you have been to my website and got the free printouts, then you can draw it yourself. What do you think it would look like? If time went by and voltage stayed at 2.5 volts, what would that look like on this graph? I'm not going to hang on this for too long because if you haven't got it, then I need to tell you. It'd just be a straight line, right? A straight line going across. So this graph would represent something called direct current. We haven't mentioned direct current, but it's actually the only one we've talked about so far. So we've been talking about, and again, hopefully all this is revision, We've been talking about how you can build a circuit using batteries. So one cell, one battery is actually called a cell in physics. So that's the circuit symbol for one cell. If we put some of those together, you get a battery. The short end represents the negative side, yeah, and the long end represents the positive side. And you attach a wire to that, and the electrons are repelled and are pushed around the circuit, and that's the only current that we've talked about. Current that flows in one direction. Do I need to complicate it? Do you remember that the electrons, by convention, we say they're travelling from positive to negative. They're not actually, but that's what you always have to think about. That is what I'm going to tell you. They travel from positive to negative. If you ever draw a circuit diagram, bear that in mind. So that was direct current. When you use a battery or cell, you are using direct current. There is a different kind of current called alternating current. So direct current is DC, alternating current is AC. It actually comes up in another module. We haven't talked about in this electricity module at all how electricity is made and how electricity comes to your house. That all gets talked about in another module, where I will tell you this story in more detail in another module, but we've just got to very briefly, I've got to tell you the little bit of the story of Tesla versus Edison. Two phenomenally talented scientists who did not get on with each other. So our story happens in the late 1800s in America. Everyone knows the name Thomas Edison. There's a whole song about him. You've probably heard of him. Thomas Edison. He invented something called the phonograph. Ooh, you may know it as a gramophone, he is saying here. Ask your great-great-grand. Look, it's amazing. Okay, says Thomas Edison. I'm amazing. Light bulbs. I invented light bulbs. Should have led with that. Thomas Edison, famous inventor of the light bulb. Nikola Tesla, you might not have heard of. He was a Serbian engineer, and he's very young, and he comes to America in the late 1800s to try and get some work. And he meets Edison, and Tesla can spot straight away that Tesla is brilliant, so he hires him. And here is an actual photo of Thomas Edison's very famous workshop in America, where loads of amazing things got discovered. So Tesla joins Edison, is inventing lab, and business is booming, they're making loads of money, but, there's a problem. Because electricity is becoming really popular, right? People are wanting this electricity in their homes. So there are power stations that generate electricity, send it to people's homes. We talk about that a lot later. Thomas Edison, brilliant inventor of the light bulb, is trying to get direct current into people's homes. And he's having a nightmare. It's not working very well. Because electricity has to be carried from power stations to people's homes using copper wires, and we've talked about resistance already this lesson, resistance being how difficult it is for current to flow. We'll talk more about this in this later module, but basically you know this already, don't you? Do you? Metal has got positive particles in it that are just vibrating on the spot. What are the names of those positive particles? Careful. So if we say that this is a very, very simple diagram of a copper wire, for example, that the electricity has to flow through, these positive particles, they are moving, but they're just vibrating on the spot to and fro. What they're called? They're not protons, right? They've still got electrons going around them. So they are a kind of atom called an ion. Do you remember that? So these are positive ions, positive metal ions. And electrons are kind of whizzing between them, and that is what current is electrons flowing. Those free electrons are flowing. But they keep colliding with the positive ions in the metal. The more collisions, the higher the resistance, the harder it is for the current to flow. It ends up all getting very hot. And yeah, it's just direct current is not a good way to get electricity into people's homes. Tesla knows this and says, hey, we should be using alternating current instead. And they basically just have this absolutely massive falling out about it. Tesla wins. The current that comes to your home now is not direct current that travels in one direction the whole time. It is something called alternating current, which is just what it says. The current just goes forwards, goes backwards, goes forwards, goes backwards, goes backwards. One of the reasons that diodes are useful, we've talked about diodes before, is because they only allow current to flow in one direction. So if you've got AC current coming out of your plug socket, which you have, and you want it to be DC current for some reason or another, you can put a diode in that circuit, and then only that direction current gets through and that current doesn't. So it's just going, you know what I mean? We'll talk about that later. Right, so what does AC current look like on a graph? Going backwards and forwards and backwards. Well, it's kind of, I don't know, it's a very physics way of putting it. It's kind of getting pushed and pulled and pushed and pulled and pushed and pulled. So you do get this proper wave. Time goes by and you get remember that the negative and positive is just the direction that it's going in. So 3 volts and minus 3 volts is the same amount of push, but it's just in different directions. In the UK, our electricity alternates, so that wave occurs 50 times a second. So if we say that that whole length of that graph is 1 second, you get 50 waves per second. And if you've brought some sort of unplugged electrical appliance with you, I've just delved under my bed to find all my long forgotten hair. I was going to call it a hair utensil, was it? I don't know. Anyway, if you have a look on your electrical appliance somewhere, this is very difficult to see, I'm sorry. It's almost like they weren't thinking of my IGCSE physics lesson when they put it on, but can you just about make out that it says 50 hertz somewhere? There it is. It's not showing up as well as it did yesterday for some reason. 50 hertz. Hertz means per second. That means that current alternates 50 times per second. But we'll go into that a lot more when we look at waves next module, so we don't need to worry too much about hertz yet. And the voltage in your home is about 230 volts. So we can correct this graph a bit better. So it goes up to 230 volts and then down to minus 230 volts and then up and then down and then up and then down, up and then down. Like I say, yeah, we won't talk too much about the hertz. We'll do that where we do waves. But that's why your electrical appliances have got 230 or maybe 240 volts written on them. God, that is so bad, isn't it? I think the light must be in a different place to where it was yesterday from the sun, because that is so rubbish. But anyway, hopefully you've got something. Oh, there we go, that's better. 230, 240 volts, because that's what's coming out. 50 hertz, that's how many waves per second, and watts we talked about last week. Phew, right. So, can we move on? Good. Phew. So what does all this mean? Well, we get to look inside a plug this lesson. I haven't actually technically got a plug for you to look at, but I did find this in a skip, which is quite useful. So I've got a plug here, which annoyingly I can't get into. They're just not made like that these days. I can't get into it. You can tell I had a go. But this plug has got 3 pins because it's a UK plug, and wires travel from each of these pins down this cable here, round and round and round we go, until if it was the actual appliance, I don't know what this is from, I don't even know if I ever knew, but that is all you would see. But if you go inside the appliance, oh, you can see that's the cable, and you do have these 3 wires coming out, and they're all attached to different places. We are going to talk about the brown wire and the blue wire first of all. So the brown wire is the live wire. The brown live wire is the one that supplies an alternating potential difference or voltage, and the blue wire is at 0 volts. Okay, so the live wire is the very dangerous one. That's got the big push to it. The blue wire's neutral, it's at 0 volts, and what happens is the difference between them is the energy that the appliance, whatever, the washing machine, is using. Is that all right? So energy comes in and then it gets used. But what happens if something goes wrong? I'm so glad you asked. Well, this is why we were talking about resistance earlier. If the live wire gets loose and touches the casing, oh, I've just seen all my comments. Hello, Molly. Oh, that's nice. I'm back again. Hopefully things will make more sense. Oh, amazing. Hello. Oh, and there's Arthur. Anyway, sorry. And Bastian's here as well. Right. If the live wire gets loose and touches the casing and you end up with current flowing like in the casing of your thing, and then you touch the casing, then that current is going to flow through you and you are going to get an extremely nasty electric shock. So this is why you've got this other wire here, a green stripy one, called the earth wire. So you'll notice that's going off into a different place, yeah? So this is, I don't know, whatever our appliance is. I should be able to work it out, really. You've got the live wire, the brown one, going into an interesting place, which is going to make the appliance work. You've got the blue wire, the neutral one, going off to the other side, make the appliance work. And this yellow and stripy green earth wire, That comes out of the cable. There we go. And it's just connected to this bit of metal, which is just stuck to the side of the case. So it's what it's doing is it's earthing the appliance. All that means is the earth wire is connected some way to the earth. So now if the live wire gets loose and touches the casing and you get these electrons flowing through your, well, sort of, you know, loose if you like, then even if you touch the casing, no offence, but the current would still rather flow through the earth wire than you, right? So, because the earth's just got more resistance. The earth can handle it. So the electrons will be flowing through the earth wire and you won't get an electric shock. It's good, isn't it? There we go. Look, PowerPoint special effects. Why is that? Yeah, like I say, it's all about resistance. Earth has a very low resistance. Cambridge, if you do the Cambridge IGCSE physics, they need you to know that, and that's why it's dangerous to have water near electricity, because water has very low resistance. So, for example, your resistance is much lower if your hands are wet. So, yeah, that's why it's more dangerous. Oh, while I'm at it, Cambridge also need you to know, I don't think Edexcel do, but Cambridge just mentioned that you need to know why it's dangerous to plug like loads and loads of plugs into the, say, like one adapter. Because it's basically because of the heat generated. So the more electrical appliances you have and the higher the resistance, then the more the heat, and eventually if you're using an appliance wrong, you can get a fire hazard. Okay, good. Snuck that in. Right, let's move on. Why do you think the earth wire is stripy? Why is the earth wire stripy? Some of you will just know this straight away, and some of you won't know. It depends if anyone in your house has got any particular conditions. Not conditions as in firm rules that you have to obey, just certain things about their body. Why would it be good to have a stripy earth wire? Why might it be very dangerous to not have a stripy earth wire? I don't know. Well, I'm about to tell you. Hello, Aris. Because colourblindness, right? So if you've got colourblind people in your family, colourblind people might struggle to tell the difference between like brown and red. I've got a lot of people in my family who just don't care about the difference between like green and brown or green and red. So obviously it would be very bad if people mistook the brown wire, which is live with 230 volts, for the earth wire, which is, you know, supposedly kind of safe and grounded. So yeah, the stripes just help with that. But Lara, what if there's a surge of current? Like, what if lightning strikes? I'm going to give you some questions to do in a minute. I feel like I've talked a lot. What if there's this surge of current that comes through the machine? Wouldn't the machine get damaged? Well, there's also, are you ready for the big reveal? Fuses. What is a fuse? Well, it's basically a very, very thin bit of wire that melts if too much current flows. Here's a picture of one. Isn't it lovely? Just a thin bit of wire, and if a lot of current flows through it, you get a lot of collisions, it gets very hot and it melts. Careful with these circuit symbols here, we haven't seen this one before. The rectangle with a line through it is a fuse. The resistor is just an empty rectangle. It's just occurred to me that that's actually quite easy to remember, isn't it? Because that is a wire just going through it. So it looks like a fuse. Yeah, they know what they're doing, don't they? These electricians. Anyway, so you need to choose a fuse that is correct for the job. There's loads of different types of fuse. In fact, you can see here in this plug, thank you Skip, you just keep giving, this has got a 13 amp fuse here. But in my hair straighteners, which I have just chucked away somewhere, wait, on this plug here, it says 5 amp fuse. So we've got a 5 amp fuse and a 13 amp fuse. What's the difference? I'm glad you asked. Here we go. I did you a scenario, a real life scenario using PowerPoint special effects. So thank you B&Q website for demonstrating to us. Other, obviously, other shops are available. You can get 1 amp fuses. You can get 13 amp, 5 amp, 3 amp. You get that beautiful pink 30 amp fuse. And you need to choose the fuse. For example, if a machine needs 10 amps to work, if this kettle needs 10 amps of current to flow through it in order for it to work, it wouldn't be any good to attach a 3 amp fuse to the plug, because as soon as 3 amps pass through that fuse, it would melt, and that would just be rubbish. So here's a kettle saying 10 amps please, and the fuse just melting. That's exactly what it is, not what it looks like. fuse melts. And the kettle's saying, I literally cannot work in these conditions. It would be a better idea to choose a 13 amp fuse. You've always got to choose a fuse that melts at a slightly higher current than the machine works at. So if it wants 10 amps, but it gets 12 amps, it's like, oh no, that stings. And then eventually, if the current gets too high, by 13 amps, that fuse is melted. And the kettle's not getting damaged because it's not having too much current kind of over its limit flowing through it, if you see what I mean. A 30 amp fuse would not be good for a kettle because you could put like 29 amps through it and it wouldn't melt, would it? So it could receive far too high a current and the fuse would still be fine, but the kettle, which is designed to operate at 10 amps, might be getting damaged. And this is exactly what would happen. It would go up in flames. I love that effect. Right, do some work, please. I've done so much talking. You've got to choose your fuse. I have said that you have fuses 1 amp, 3 amp, 5 amp and 13 amp to choose from. I've given you the equation that we looked at last week. Power equals current times voltage. I would like you to look at these 4 scenarios and choose a fuse. So if you had... Oh, sorry, I should have said to bring a calculator. Can you bring a calculator? If you've got an 800 watt toaster with a potential difference voltage of 230 volts, you need to work out what the current is flowing through that toaster and then say which fuse would you use. Question number 2, a 2.3 kilowatt kettle with a potential difference of 230 volts. You have to choose which fuse you would use for that too. Number 3, a 1 kilowatt hairdryer plugged into the mains in the UK. Choose which fuse you'd use. And question number 4, what? You've got a parallel circuit. Oh, that was a while ago, wasn't it? A parallel circuit with 3 branches. There's a bulb and an ammeter on each branch. And all the ammeters say 0.7 amps. And there is a fuse sort of outside the branches, just next to the battery. What would you make that fuse? Choose. Choose or lose. Okay, I'm going to stop now. I'm just going to let you do it. My friend can't see blue on purple or red on green. Ah, right, yeah, exactly. So, okay, yeah, that's definitely why if it was just like a red live wire and a green earth wire, that would not be good for them. So most people comment on these videos now, but I have got a post up on my Facebook page. If you don't like to or you can't comment on YouTube, you can go over to my Facebook page and there's a post saying, comment on this post if you're watching live and I'll say hello to you at the end. Jacob sometimes does that. Bastian used to, but Bastian's here now. Bastian's jumped over. How are you getting on? Seconds. This will stay on YouTube until, I don't know, they take my channel down for reasons or the end of YouTube, so you can always come back to it if I go too fast for you. Okay. I'll start going through it because I want to get to the quiz. The quiz, have you got an electric shock or not? Okay, so you've got an 800 watt toaster with a potential difference of voltage of 230 volts. You've got to do a little bit of rearranging of this equation because you need to find the current flowing through the toaster. So it's current equals power divided by voltage. and it's not a trick question, it's just 800 watts divided by 230 volts. So there's a current of 3.5 amps flowing through that toaster. Be careful, you might think, oh, 3 amps is the closest, but obviously that's no good because that fuse melts at 3 amps and you've still got half an amp to go before your toaster works properly. So you need to choose the one slightly above 3.5 amps, and the one slightly above, or the next one up if you like, is 5 amps. So you've got to choose the 5 amp fuse. Number 2, I've got to throw this in to try and catch you out so that you don't make that mistake in the exam. Did you see that kilowatts is 1,000 watts? Yeah, like a kilogram is 1,000 grams. So it's current equals power divided by voltage again, but it's 2,300 watts because that's the same as 2.3 kilowatts. Divided by 230 volts, which gives you 10 amps. So you had to choose the 13 amp fuse, just like a kettle scenario. And here, you just had to know that the mains in the UK is 230 volts. If you use 240, probably be okay as well. So that was 1,000 watts divided by 230 volts, which is 4.3 amps. So you choose the 5 amp fuse. And this one, did you remember that current splits in a parallel circuit, but then it all comes back together again? So the total current in that circuit, the total current passing through that fuse, is 0.7 amps times 3, which is 2.1 amps. So you had to choose the 3 amp fuse. Whew. I'll hover you very quickly on that if you want to write down the answers. 3.5 amps, 10 amps, 4.3 amps, and 2.1 amps. So 5, 13, 5, and 3 are your fuse choices. Right, yeah. I've got all these pictures of plugs, different scenarios, and some of them are safe and some of them are not safe, and I want you to try and spot which ones are safe and which ones are not safe. But first, I'm going to give you a very quick peep at a different bit of my house. I know, you love it. You love it when we go on tour. So you've got these things called circuit breakers that one of the specifications, maybe both actually, maybe both now, need you to learn about. A circuit breaker works in a very similar way to fuses, but instead of being in the plug, they are where the electricity actually comes in. And an RCCB is a different type of circuit breaker, residual current circuit breaker. It detects a difference in the current between the live and the neutral wire and switches off the circuit. So basically, the RCCB, it can tell if the current is flowing through the earth wire. Yeah, and if it detects that current is flowing through the earth wire, it just shuts everything down, because we've been acting like, it's totally fine, the current just flows through the earth wire, not through you. It's still not good though, is it? That's still not an appliance working properly, and that needs to be sorted out. So if it detects that an earth wire is sort of being used, I suppose, then it switches everything off. Right, come on. Yesterday when I did this, the video went ever so slightly sticky, but we got through it. It was fine. So I'm going to try it again. I'm going to take you down to where the electricity comes into my house and show you my circuit breakers. You're still there? Okay, this is good. This is good. You're still there. Hello, just showing everyone our circuit breakers. You ready? Oh, welcome to my porch. Yeah, we've got stuff to take the chair to shop. We've got a football, and we've got this thing. Let's go inside. Look, danger. 130 volts. See, because that is the voltage of electricity that comes into your home. And if I flip this little thing, way, aren't they pretty? So these are all my circuit breakers here. We've got the main switch, and then basically the electricity when it comes into your home is split into lots of different little circuits. Look, these have been beautifully labelled. Kitchen sockets, upstairs lights. So if this circuit breaker detects that there's a problem with the upstairs lights, that maybe the current isn't flowing as it should, then all the upstairs lights go off and I go, oh, what's going on? And I come here and I flick that switch up again and I hope that it's all just sorted itself out, which it usually has. And if it doesn't, if it keeps getting switched down, then frankly, I have to call someone in. Yeah, so that's it. They're nice, aren't they? Look at that. We made it real. Okay, come back upstairs with me. Makes my husband very uncomfortable when I bring you out of the office. He might be seen. He doesn't want to be seen. Right, so we're very different in that respect. Okay, we've nearly covered the whole plug. Nearly. There's just one extra little thing I need to mention. So this is a nice little diagram of plugs. Do you remember all this stuff? You've got the cable going in. You've got the cable grip, just the thing that keeps the cable in place. You've got the neutral blue wire going off to the left. You've got your live earth wire, which is brown, going off to the right, which is attached to a fuse, because obviously that's what you would want to melt to cut the circuit to the live wire. Between the live wire, I should say, and the appliance. You've got your green and stripy yellow earth wire. And there's just one more thing we need to talk about before we do this little quiz to end. This symbol, this white square inside another white square, means that an appliance is double insulated. If you remember, we were talking about insulation before. An insulating material is just one that doesn't allow current to flow through it. So there's a layer of insulating material all around the appliance, so technically they don't need an earth wire. I mean, they usually have an earth wire anyway, but because if there was, there wouldn't be current kind of flowing through the casing, so technically if you touched it, it wouldn't flow into you. And again, if you've got your unplugged electrical appliance with you, you can have a look. I was delighted today to find that these ancient hair straighteners just keep giving. Can you see that? Can you just make that out? That little square inside a square. So these hair straighteners are double insulated. So if I ever use them again, I can use them safe, that if something goes wrong, I won't get electrocuted. Right, okay. Okay, so are you ready for your quiz? We're gonna play shock or safe. So I'm going to show you some different things. If you've got the printout from my website, then you've got this in front of you and you can draw some notes on it if you like. Is this a safe situation, or are you going to get an electric shock, or is it a trick question? So here we are. You've got a plug with a neutral wire going off to the left, a live brown wire going off to the right, attached to a fuse, and you've got an earth wire, which is stripy yellow and green, going off to the top, attached to some Christmas lights. Is that a safe situation, or is that going to give you a shock? Safe or shock? Safe or shock? Do. Let's play safe or shock. Just made that up. I did. I know. Yeah, that's fine, isn't it? That's totally fine. We've got the fuse in place, so if it's not going to get damaged because that fuse would melt before the lights got damaged. You've got the earth wire nicely connected. Yeah, all lovely stuff. Okay, what about this one? You've got a neutral wire going off to the left, a live wire, which is brown, going off to the right, attached to a fuse. You haven't got an earth wire going at the top, and it's attached to this washing machine. Safe or shock? Safe or shock? Let's play safe or shock. Boo! This one is... it's not particularly safe. It could give you an electric shock, or it could damage your appliance. It's not earthed, so yes, it is really quite a dangerous situation, I suppose. I mean, you would hope that the fuse does its job, but if the live wire, even if there wasn't too much current flowing, if the live wire came loose, it's possible that you could get an electric shock from electricity flowing from the casing into you. This is not double insulated, is it? What about this one? Neutral wire going off to the left, live wire going off to the right, attached to a fuse, no earth wire, vacuum cleaner with a little white square inside of a white square on it. Is that safe or shock? Safe or shock? Let's play. Okay, it's have you got it? It's safe. That one is fine because it's double insulated, so it doesn't technically need an earth wire, right? Because if the live wire ends up touching the casing is double insulated, so that electricity is not going to be able to flow from the live wire to you because of that insulation in the way. What about this one? Neutral wire going off to the left, live wire going off to the right, not attached to a fuse, earth wire going at the top. Is that safe? Are you going to get an electric shock? What's going to happen there? What is going to happen if you plug that into your mains and turn it on? What is going to happen? Let's say it's connected to a toaster. What's going to happen to your toaster when you plug that on? Plug that in. What's going to happen if you touch the toaster? There is no fuse. Well, the temptation this is where people lose marks at GCSE. The temptation is to say that, well, that's not right, so I would get an electric shock. That's not technically true. What would happen is it just wouldn't work, right? Because the current has to flow from the live wire through the fuse to get to the appliance. So this is kind of the same as having a fuse that has melted, right? The fuse isn't there, so the circuit isn't complete, so you wouldn't have any electricity flowing. So if you got asked that in an exam, the classic wrong answer that everyone would say would be, you'd get an electric shock, or the appliance would break, but actually nothing would happen. What about this one? Live brown wire going off the left, neutral wire going off the right, attached to the fuse, earth wire going up to the top, and it's a double insulated kettle. Is that safe or is that dangerous? It's a bit of a weird one, this, isn't it? What would happen in this scenario? What would happen if you touched the casing if there was a problem? What would happen if lightning struck and a big surge of current went through it? Have you spotted the problem? There is a problem, isn't there? These live wires and neutral wires have got mixed up. So what would happen? Well, it would work because you have got a complete circuit. So that would operate. It wouldn't necessarily give an electric shock, actually, would it? Because it's double insulated. But what it would mean was that if a huge surge of current happened, then the current would still flow through the live wire and it could really damage your appliance. So it's important to get the live and the neutral wire. And also, yeah, obviously if the live wire came loose, that would be bad. Here we go, here's another one. Neutral wire going off the left, live wire going off to the right, attached to a fuse, and you've got the earth wire, but it's very frayed. What would happen in that situation? Why is that a problem? So I gave you a clue for this earlier. Is it a problem? Maybe it's not a problem. That is a problem, isn't it? Because what do we know about wires when they're very, very thin or they're very, very long? They've got a very high resistance. So that is quite a dangerous situation because current is flowing through really, really tiny little bits of wire, which, like Cambridge want you to know, can generate some heat. So it could be a fire hazard, or it could just eventually mean that the earth wire comes undone and then your appliance isn't earthed, which is bad because this one isn't double insulated. So that's why that one's dangerous. What about this one? Neutral wire going off to the left, live brown wire going off to the right, attached to a fuse, earth wire going up the top. Any problems there? I haven't put any cable grips into any of these diagrams, have I? So well done if you're saying that one of the problems might be that there isn't a cable grip. That I just haven't considered the cable grip actually. But obviously it is important that these things are held in place so that they don't end up getting wiggled out of position. That one is fine. Yeah, it's fine. That's exactly what a plug should look like. What about this one? All right, so this one's not obviously right. You've got a neutral wire going off the right, a brown live wire going off the left. You've got an earth wire in place, but instead of a fuse, you've got a metal screw. Why is that a problem though? What's going to happen if we plug that in? What's going to happen if we plug it in? What's going to happen if there's a lightning strike or something and you get a big surge of current going through the appliance? You might think that's ridiculous. I never show images online that I don't have the rights to show, you know, like copyright laws and stuff. But I don't know where this image came from, and it's just too good to not show you, so I'm just going to wait and see if someone tells me off for showing you it. That is an actual, real true thing, where someone got a metal drill bit and put it in where the fuse should be. Well, that appliance is working, isn't it? It's not like where we didn't have a fuse. That is a full, complete circuit. Electricity can flow through the drill bit. That's incredibly dangerous, isn't it? For loads of reasons. First of all, you've got this exposed metal. So if someone came and touched that drill bit there, they could get an electric shock because current might flow through them. Also, that is not a fuse, so it's not going to melt. So it's not going to protect the appliance either. So if there was a huge surge of current, I don't know how many amps you can get through a drill bit before it melts, but it's a lot. It's a lot. Nobody wants to see that. So that is why it's really important to learn about electricity. So I thought that's a nice way to end our final lesson on electricity, kind of, apart from when we learn about how it's generated in power stations and stuff. But yes, that is the end of the lesson. Thank you so much for coming. I'll go over to my Facebook page and see if anyone has left me any comments, but it has been nice to see a few comments popping up here. Right, yeah, so now is the time, I suppose, when I should say, if you're enjoying these lessons, now would be a good time for you to tell other people about them, because I'm taking, if you're watching live, I'm taking 2 weeks off for the Easter holidays, do some parenting or whatever, and then we're coming back with waves. We start in waves. There's loads of practical activities for waves. We're going to make rainbows and listen to sound waves and look at all the differences between all the different waves. I love the waves module. I'm excited about it. So yes, if you want to support me, if you are enjoying the fruits of my brain, what a gross way of putting it, then you can support me with £5 a month. That is how it works. So you go to my about section of my YouTube channel and you find this link to this website called Coffee, and I would just say, if everyone sends me £5 a month, that is enough to keep these lessons going. And this is probably sort of the best value one, I suppose, because I am actually trained to teach physics to GCSE and A level. Like I had to train to do that. I had to be a physics teacher for a while, and I'm just kind of putting that into the internet for free. So the lessons are free, the printouts are free. There is a homework PDF on my website as well, with loads of different past paper questions and further reading that you can do to kind of, because you can't really learn IGCSE physics just from one lesson a week, right? Yeah, and it's all free, so go to my Coffee page from my About section, look up this link to Coffee, send me £5 a month, and I will send you nice things to say thank you. I will send you some diffraction glasses. Arthur, I can see your comment, but I'm not going to reply at the moment. I might put up a post about it later. Where am I? Diffraction glasses? Oh, here they are. I call them rainbow glasses, but actually they're diffraction glasses, which we will learn all about when we learn about waves, and we'll do some activities. But yeah, it's a good time for you to get these rainbow glasses because they're awesome and very appropriate. And I will send you a description of how they work, which again relates to the IGCSE that you might end up doing. And I send Theatre of Science magazine out as well. Theatre of Science magazine takes me just forever. It takes me such a long time, but I'm really happy with it. It's the only thing I make in Theatre of Science that I'm truly happy with, because I get it exactly how I want it before I send it to you, which does mean that my supporters have waited a year for it this time, but it's going to be really good. So sorry, message me if you've got any issues with that. But anyway, if you sign up to support me now, you'll get a past issue, either on mould, or if you sign up with £6 a month, you'll get a past issue on sleep as well. They're very good, I have to say. They've got comics in them. They've got Choose Your Own Adventures, these two. They come with little free gifts. So this one comes with a home compostable plastic bag so you can grow some mould and identify it. And the Sleep magazine comes with some organic lavender, a little bit of fabric so you can do some sewing. The next issue, if you're watching live, is about spies. And it's got James Bond jigsaw and it's got a little bit of wax, and you can fold up a letter like Mary Queen of Scots did and then seal it with wax. And it's got a huge long story about like the American Civil War, which I didn't know anything about. So I've really enjoyed myself with it. I've had a great time. And it is very nearly ready. So if you sign up to support me now, you'll get all that stuff, but you'll also then just be on the list to get Theatre of Science magazine when it next comes out, which will be soon. Oh, right, Edmund! Oh, I've just come to my Facebook page to find the comments from the people that are wanting to comment on Facebook. And here's Edmund and Freya. Freya saying, we enjoy the fruits of your brain. That's nice. I'm glad. Is it gross? Seems a bit... Anyway. I'll move on from that. Edmund is watching. He thinks he has worked out the answer to his question from last week. He says that yes, IVT, which is an equation for energy, does equal mc squared, and his reason is that energy cannot be created or destroyed, but it can be converted into matter, so the m on one side of the equation represents how much mass there would be if there was electrical energy on the other side. Yeah, I think you're right. I can't see a problem with that. Notice how I phrased it. I can't see a problem with that, no. I think that's good. He wants to point out that Thomas Edison was not the original inventor of the light bulb, as a version of them already existed, but he improved on the design and made them safer and less likely to explode. Okay, the inventor of his kind of light bulb. Hello, Jacob. I didn't tell you that Thomas Edison electrocuted an elephant. That's not a nice way to end this module, is it? I'll tell you about it next time. He wanted to use DC and thought that was the way forward, even though it definitely wasn't. if you're using DC, it can't travel far enough. You end up with power stations having to be like all over the place next to people's houses. Doesn't work. Tesla knew that AC was the answer. This elephant killed their trainer because it's the 1800s. Can you imagine what elephants had to put up with? Probably even worse than now. This elephant had killed its trainer and had to die. And Thomas Edison stepped forward and said, I'll electrocute it for you. And electrocuted it on telly with Tesla's AC current to show the world, look how dangerous AC current is. It will even kill elephants. So you should choose my DC current instead. He used to kidnap cats. I can't tell the kids this stuff. Awful. Not a pleasant man. Anyway, on that note, on the cat kidnapping note, I will go. Just checking that no one's left me any more comments. Good. Right. Yeah, I'm going to go. Oh, does Tesla have anything to do with modern car brand Tesla? Yes, I think so, Arthur. I'm not entirely sure. I haven't looked into it. But I would be very surprised if there wasn't a connection there. Yeah, if Tesla hadn't wanted to stick Tesla's name on, because they're electric cars and electricity, Tesla, very cool, big deal. Yeah, probably. Don't know how happy Tesla would be with that, but it's too late now. Right, yes, I'm going to go. Thank you so much for joining me. So this was my last IGCSE lesson of the electricity module. We've now done 2 modules, forces of motion and electricity. They're both on my website with all the updated homework PDFs for watching on catch up if you want to. And then, yes, next week we start, in 2 weeks' time we start waves. I'll see you all then. I can't wait. Bye.